UL specifies neutral ground bonding to prevent electrical shock hazards. This is achieved by ensuring the neutral conductor is at the same voltage as the grounding system, which eliminates the potential for a dangerous voltage difference. Neutral ground bonding is typically performed during production. Firstly, it ensures uniformity and consistency in the electrical system. Secondly, it simplifies testing and troubleshooting. Thirdly, it reduces the risk of incorrect bonding during field installation. If testing is required with the neutral bonded to ground, there are several methods that can be used. Firstly, an ohm meter can be used. Measure the resistance between the neutral and ground terminals. A reading close to zero indicates a good bond. Secondly, a ground fault indicator can be used. Connect the ground fault indicator between the neutral and ground terminals. A reading above a predetermined threshold indicates a ground fault. Thirdly, a ground fault detector can be used to detect and locate ground faults in the system. In addition to disconnecting the neutral ground bond, there are other possible resolutions. Firstly, the ground fault current path can be increased. This can be achieved by using larger ground conductors or shorter ground loops. Secondly, the neutral can be isolated. This involves using an isolating transformer to separate the neutral from the grounding system. Thirdly, a ground fault circuit interrupter, or GFCI, can be installed. This device will trip the circuit if it detects a ground fault. Testing procedure should be modified to disconnect the neutral ground bond before testing the generator. This prevents the ground from becoming a current-carrying conductor and eliminates the potential safety hazard. Ensure that the generator is properly grounded to protect against ground faults. Use a reliable method to test for ground faults during testing. Implement safety protocols to minimize the risk of electrical shock hazards during testing. It is crucial to understand the implications of neutral ground bonding in generator systems. Firstly, consider the purpose of grounding. Grounding provides a low impedance path for fault currents to return to the source, allowing protective devices like circuit breakers to quickly trip and clear the fault. Secondly, understand the role of the neutral. In a Y-connected system, the neutral point is the common point of the three-phase windings. It is typically grounded to provide a stable reference point for the voltage. Thirdly, consider the impact of bonding. Bonding the neutral to ground ensures that the neutral conductor is at or near ground potential. This is important for personnel safety, as it minimizes the voltage difference between the neutral and any grounded surfaces. The National Electrical Code, or NEC, provides guidelines for grounding and bonding electrical systems. It specifies when and where neutral ground bonds are required. Consult the NEC for specific requirements in your application. When testing generators, it is important to consider the potential hazards associated with ground faults. A ground fault occurs when current flows from a phase conductor to ground. This can create a dangerous shock hazard if someone comes into contact with the faulted equipment. To minimize the risk of ground faults, use a ground fault protection system. This system typically consists of a ground fault relay and a current transformer. The current transformer monitors the current flowing in the grounding conductor. If a ground fault occurs, the relay will trip a circuit breaker, interrupting the flow of current. In addition to ground fault protection, use appropriate personal protective equipment, or PPE, when working on electrical equipment. This includes safety glasses, gloves, and insulated tools. Regularly inspect electrical equipment for damage. Look for frayed wires, cracked insulation, and loose connections. Repair or replace any damaged equipment immediately. When testing generators, use a resistive load bank. A resistive load bank provides a stable and predictable load for the generator. This allows you to accurately measure the generator's performance. Connect the load bank to the generator using appropriate cables and connectors. Ensure that all connections are tight and secure. Monitor the generator's voltage, current, and frequency during testing. If any abnormalities are detected, stop the test immediately and investigate the cause. When working with high-voltage generators, exercise extreme caution. High voltage can be lethal. Only qualified personnel should work on high-voltage equipment. Follow all safety procedures and use appropriate PPE. If you are unsure about any aspect of generator testing, consult with a qualified electrical engineer. They can provide guidance on the best practices for testing and safety. The initial observation of fluctuating video monitor behavior points to a potential issue with the power quality or grounding within the test setup. This symptom could be indicative of several underlying problems, including but not limited to ground loops, electromagnetic interference, or voltage instability caused by the grounding configuration. It's crucial to isolate and address the root cause rather than merely reacting to the symptom. The discovery of a large amount of current flowing to ground, directly correlated with the bonding of the generator neutral to the generator housing ground, strongly suggests that the grounding system is acting as an unintended current path. This is a direct consequence of creating a parallel path for current flow, one through the intended neutral conductor and another through the grounding conductor. This situation can lead to several undesirable outcomes, including elevated ground potential, increased electromagnetic interference, and potential safety hazard. The directive from UL and CSA regarding neutral ground bonding stems from safety considerations aimed at minimizing the risk of electric shock. The fundamental principle is to maintain all exposed conductive surfaces at or near ground potential. However, this practice is typically intended for service entrance equipment or separately derived systems, not necessarily within the test setup of a generator, where alternative grounding strategies may be more appropriate. The immediate action of ceasing operations and performing an ohm test on the generator, transformer, switchgear, and load bank was a prudent step. While an ohm test provides valuable information about continuity and insulation resistance, it might not reveal the underlying cause of the current flow issue, especially if the problem is related to impedance or stray capacitance effects under load conditions. The concern about potential voltage hazards to personnel and equipment is well founded. An improperly grounded system can lead to elevated touch potentials on equipment surfaces, increasing the risk of electric shock. Moreover, circulating ground currents can induce voltages in nearby circuits and cables, potentially disrupting sensitive electronic equipment. Addressing the question of why UL specifies bonding the neutral with the ground involves understanding the context in which this requirement is applied. In general, neutral ground bonding is intended to establish a low impedance path for fault currents, facilitating the rapid clearing of faults by overcurrent protection devices. This practice is particularly important in service entrance equipment where the utility transformer secondary is connected to the building's electrical system. However, in the context of generator testing, the grounding requirements may differ depending on the specific test setup and the applicable standards. The question of whether neutral ground bonding should be done in the field versus production is a matter of practicality and safety. In production, neutral ground bonding can be implemented in a controlled environment with standardized procedures and quality control measures. This ensures consistency and minimizes the risk of errors. In the field, however, neutral ground bonding may be more complex due to variations in site conditions and the potential for human error. It is generally preferable to perform neutral ground bonding in production whenever possible. If testing requires the utilization of the neutral, several methods can be employed to minimize the risk of ground currents and ensure accurate measurements. Firstly, an isolated neutral system can be used. This involves isolating the neutral conductor from ground, except at a single point, typically at the generator. This prevents ground currents from flowing through the neutral conductor. Secondly, differential current measurements can be implemented. Use a differential current probe to measure the current flowing in the neutral conductor and the grounding conductor. If there is a significant difference between the two currents, it indicates a ground fault. Thirdly, high impedance grounding can be employed. A high impedance resistor is inserted in the grounding path to limit the ground fault current. This reduces the risk of equipment damage and personnel injury. The disconnection of the neutral ground bond, as performed, was a valid step in troubleshooting the problem. However, it is important to carefully consider the implications of this action. Disconnecting the neutral ground bond can increase the risk of voltage fluctuations and ground faults. It is essential to implement appropriate safety measures to mitigate these risks. Other possible resolutions beyond disconnecting the neutral ground bond include several approaches. Firstly, consider improved grounding practices. Ensure that the grounding system is properly designed and installed. Use low impedance grounding conductors and minimize the length of grounding paths. Secondly, employ electromagnetic interference or EMI filtering. Install EMI filters on sensitive equipment to reduce the impact of noise and interference. Thirdly, implement surge protection measures. Protect equipment from voltage surges and transients with surge protection devices. In addition to the recommendations provided, it is crucial to perform a thorough analysis of the entire electrical system to identify potential sources of ground currents and voltage fluctuations. This analysis should include a review of the grounding system, wiring practices, and equipment specifications. It is also important to consult with a qualified electrical engineer to obtain expert advice and guidance. The observation of fluctuating video monitor behavior and the subsequent discovery of a large amount of current flowing to ground when the generator neutral was bonded to the generator housing ground is indicative of a complex grounding issue. The directive from UL and CSA to bond the neutral to ground is rooted in safety principles aimed at minimizing electric shock hazards, but the application of this principle must be carefully considered in the context of generator testing. In production environments, neutral ground bonding is often performed to ensure uniformity and consistency, simplify testing, and reduce the risk of incorrect bonding during field installation. However, during testing, alternative grounding strategies may be more appropriate to avoid unintended current paths and potential safety hazards. Several methods can be used to test with the neutral connected to ground, including ohmmeter measurements, ground fault indicators, and ground fault detectors. These methods can help identify and locate ground faults in the system. Other possible resolutions include increasing the ground fault current path, isolating the neutral, and installing a ground fault circuit interrupter, or GFCI. However, each of these solutions must be carefully evaluated to ensure that it is appropriate for the specific application and that it does not introduce new safety hazards. The decision to disconnect the neutral ground bond before testing the generator was a prudent step, as it prevented the ground from becoming a current-carrying conductor and eliminated the potential safety hazard. However, it is important to ensure that the generator is properly grounded to protect against ground faults and to use a reliable method to test for ground faults during testing. It is also essential to implement safety protocols to minimize the risk of electrical shock hazards during testing. In addition to these measures, it is important to consider the following factors. Firstly, the impedance of the grounding system should be minimized to reduce the voltage drop along the grounding conductors. Secondly, the grounding conductor should be sized appropriately to carry the maximum fault current. Thirdly, the grounding system should be regularly inspected and tested to ensure that it is functioning properly. By carefully considering these factors and implementing appropriate safety measures, it is possible to safely and effectively test generators while minimizing the risk of electrical shock hazards. The situation described highlights a common challenge in electrical systems, balancing safety requirements with operational needs. The UL and CSA directives regarding neutral ground bonding are primarily aimed at ensuring personnel safety by minimizing the risk of electric shock. However, in specific applications such as generator testing, these directives may need to be adapted or supplemented to address unique circumstances. The key is to understand the underlying principles and to apply them in a way that ensures both safety and functionality. When testing generators, it is important to consider the potential for ground faults, which can occur when current flows from a phase conductor to ground. Ground faults can be caused by a variety of factors, including insulation failure, loose connections, and equipment damage. To mitigate the risk of ground faults, it is important to use a ground fault protection system, which typically consists of a ground fault relay and a current transformer. The current transformer monitors the current flowing in the grounding conductor, and the relay trips a circuit breaker if a ground fault is detected. In addition to ground fault protection, it is important to use appropriate personal protective equipment, or PPE, when working on electrical equipment. This includes safety glasses, gloves, and insulated tools. It is also important to regularly inspect electrical equipment for damage and to repair or replace any damaged equipment immediately. When testing generators, it is important to use a resistive load bank to provide a stable and predictable load for the generator. This allows you to accurately measure the generator's performance. Connect the load bank to the generator using appropriate cables and connectors and ensure that all connections are tight and secure. Monitor the generator's voltage, current, and frequency during testing, and stop the test immediately if any abnormalities are detected. When working with high-voltage generators, exercise extreme caution as high voltage can be lethal. Only qualified personnel should work on high-voltage equipment, and all safety procedures should be followed. If you are unsure about any aspect of generator testing, consult with a qualified electrical engineer for guidance. The root cause of the excessive ground current, given the described setup, most likely stems from circulating currents arising from multiple ground paths. In a properly functioning system, the neutral conductor should carry the unbalanced load current back to the source, and the grounding conductor should only carry fault current during a ground fault condition. However, when the neutral is bonded to ground at multiple points, a parallel path is created for the neutral current to flow through the grounding conductor. This can lead to several problems, including increased ground potential, electromagnetic interference, and potential safety hazards. To address this issue, it is important to minimize the number of neutral ground bonds in the system. In general, only one neutral ground bond should be present, typically at the service entrance or at the generator. Additional neutral ground bonds can create circulating currents and compromise the integrity of the grounding system. In the context of generator testing, it may be necessary to temporarily disconnect the neutral ground bond to isolate the generator from the rest of the system. This can help to identify and eliminate sources of ground current. However, it is important to ensure that the generator is properly grounded to protect against ground faults, even when the neutral ground bond is disconnected. This can be achieved by using a dedicated grounding electrode system for the generator. In addition to minimizing the number of neutral ground bonds, it is also important to ensure that the grounding conductors are properly sized and installed. Grounding conductors should be sized according to the requirements of the National Electrical Code, or NEC, and they should be installed in a way that minimizes impedance. Low impedance grounding paths are essential for ensuring that fault currents can flow quickly and safely back to the source. In conclusion, the situation described highlights the importance of understanding the principles of grounding and bonding in electrical systems. By carefully considering the grounding configuration and implementing appropriate safety measures, it is possible to safely and effectively test generators while minimizing the risk of electrical shock hazards. The NEC Article 250 provides comprehensive guidance on grounding and bonding requirements for electrical systems. It is important to consult the NEC for specific requirements in your application. When working with electrical systems, it is always best to err on the side of caution. If you are unsure about any aspect of grounding and bonding, consult with a qualified electrical engineer for guidance.